Okay, let's begin. Go ahead and head into chapter 9 here. We talked about doing Lewis dot structures, kind of how bonds are made, determining kind of the basic structure. So now we want to get into the actual shape, the physical three-dimensional shape that a structure or a compound might have, a molecule might have. So getting into molecular shape. And the shape of something plays a role in how it reacts, how it interacts with other molecules, whether bonds will be broken, whether it's going to form new bonds, things like that, whether it'll be polar or non-polar. So all of those components lead to, like, its shape is governs a variety of things. So, and with that, we have to look at the electrons that are involved in bonding, so like shared pairs of electrons, but also looking at non-bonding electron pairs and how those things influence the overall shape of a molecule. So let's talk about what the things that determine the shape of a molecule. So it comes down to where the electrons are, because electrons are negatively charged. They're going to repel each other, and so depending on how many bonding and non-bonding pairs, they're going to repel each other. So here we have an example of ammonia, and ammonia has three shared pairs of electrons and one unpaired share or non-bonding pair of electrons. So we assume that all the electron pairs are placed as far as possible away from each other because they're negative, and that's going to help us predict the overall shape. So we can refer to the electron pairs as electron domains. And so when we look at electron domains, so we've got lone pairs or unbonding pairs, so those behave, and then a double or triple bond, all the electrons are shared between two atoms and therefore behave as one electron domain when we're talking about that central atom. So looking at this central atom here, the letter A, it has three shared bonding pairs and one unshared bonding pair on that central atom. And so it has a total of 4 domains, 3 shared and 1 unshared. So this leads us to the valence shell electron pair repulsion theory. And this is the idea that geometries can be determined using the idea that electrons repel each other, that they're trying to minimize their proximity to one another. And so you get maximum repulsion, looking at these electrons. So we've got a number of electron domain geometries. So if you have 2 electron domains, it's going to be linear. If you have 3, it's going to be trigonal planar. If you have 4, it's tetrahedral. 5, it's trigonal bipyramidal. And 6 electron domains, it's octahedral. Now, so these are electron domains. Sometimes electron domains can be lone pairs. Other times the electron domains can be shared pairs of electrons. And that's where we'll get a variety of actual molecular geometries. But these are electron domain geometries that are being described here. So in this case, you've got the ammonia, you have the Lewis dot structure for ammonia, and then you just count the number of electron domains around it. And in this case, there are 4 electron domains. There are 3 shared electron domains and 1 unshared electron domain, but they all count, so a total of 4 electron domains. So the electron domain geometry would be tetrahedral. Now, the molecular shape is not tetrahedral, and that's what we'll lead to. So we get the formula, we make the Lewis dot structure, we count the number of electron domains, and then we figure out what the molecular geometry is. And they're going to be slightly different. So the electron domain geometry is often not the shape of the molecule. And we'll look at a table that kind of describes those. The molecular geometry is what is defined by only the positions of atoms versus where the non-bonding pairs are as well. So in the case of tetrahedral electron domain, if all of the electrons are shared pairs, then the actual shape, the molecular geometry, will be tetrahedral. But let's say you have like ammonia where it has 3 shared pairs and 1 unshared. Well, that is, the electron domain is tetrahedral, but the molecular shape of the 3 bonding atoms is going to be trigonal pyramidal. And then for if two domains are shared or are bonding pairs, and then two are non-bonding pairs, then the shape is going to be bent. And for linear, well, it really just comes down to it's linear. There's no, there's another way to do that one. The only two atoms in the molecule, if there are only two atoms in a molecule, then of course the shape will be linear. Yeah, that's the only option. Now, if you have a trigonal planar domain geometry, there's two options available. You can have trigonal planar if all of them are bonding pairs, and then if one is an unshared pair, then you're going to have a bent shape. All right, now when you have non-bonding pairs, it is going to impact what the bond angle will be, because the electrons are unshared pairs of electrons have kind of a greater kind of push or repulsion on the bonding pairs. So if you look at the methane molecule on the left down there, the bond angles between all the hydrogens is 109.5. All the shared electrons in the bonds are repelling each other equally to get an angle of 109.5. Now with ammonia, where you've got one lone pair of electrons and then the rest are bonding pairs, the lone pair actually kind of pushes those hydrogen bonds closer to each other than the hydrogen are in the methane. And then even greater, or smaller I should say, bond angle for a water molecule with those two lone pairs sitting out on the oxygens. Because there's just kind of a greater repulsion, excuse me. So if you look at this diagram, so between two nuclei, the bonding electrons have kind of a more focused area where the electron pair will be, where with a non-bonding pair, it's a broader area where that non-bonding pair can be, and therefore greater repulsion to other electrons in bonding pairs. And that's kind of what I said. Okay, when you have multiple bonds and different bond angles, so double and triple bonds, they create a greater electron density in that area. So you've got this double bonded oxygen. Well, there's 4 electrons shared between that carbon and that oxygen, so therefore it's going to have greater repulsion to those single bonds between the carbon and the chlorine. So therefore, the carbon and chlorine bonds are closer to each other, greater distance between the oxygen and the chlorine. So the number of electrons in domains will affect the bond angle in the process. All right, some of the other ones, other geometries. So when you have tetrahedral electron domain geometry, if 4 are bonding domains and 0 non-bonding, then the shape is tetrahedral. Then it moves to trigonal pyramidal, and then next to bent, where you have 2 non-bonding and 2 bonding pairs. All right, a more elaborate one is the trigonal bipyramidal electron domain, and this one you have different positions. You have the axial positions of the atoms, and then you have the equatorial positions, and we'll use those to kind of describe the overall shape. So lower energy conformations result from having non-bonding electron pairs in equatorial rather than axial. So you're not going to have a non-bonding pair starting off on an axial position, so they're going to be on the side to start with. And so shape-wise, so to start with, if you have 5 bonding domains, you're going to have a trigonal bipyramidal shape. But the first lone pair is going to exist coming off of the central atom on the equatorial plane, and that shape is going to be seesaw. And then if you go to 2 non-bonding domains, you're going to have, it's going to be a T-shaped, and then 3, and notice how they're all those non-bonding pairs are on the equatorial, so then your last one is going to be a linear shape. And then going along, you then have your octahedral, so 6 domains to start with. The whole shape is octahedral, but then you move to 1 non-bonding domain, and that's going to be coming off of either the top or the bottom there, and you're going to get square pyramidal, and then the last one will be square planar, so lone pairs coming off of that. So when you think about large molecules, So large molecules have a three-dimensional shape. They have a geometry. But when we think about the geometry, we really should break it down per central atom. So we've got this larger molecule here. And if we break it down, we can look at the first carbon and talk about its geometry being tetrahedral because it has 4 bonds. But then the second carbon, that's double bonded to the O and to the other O and then to the carbon, is more trigonal planar. So you can kind of develop an understanding of the molecular geometry just looking at the individual atoms. And so this helps us understand what the overall three-dimensional shape of a large molecule would look like, and then also how it might react to other things when it comes in contact with it. So that's it for today, and we'll see you tomorrow for the quiz and going into Chapter 9.